For day 91, we're dealing with improper integrals. This is the first of 2 days. Way back in chapter 4, we learned that continuity implies integrability, and that's a fun word to say, but what that means is that you can take the antiderivative as long as things are continuous. So if a function is continuous on a closed interval, then f is integrable on that closed interval. In other words, the antiderivative exists. But there are many cases where these two requirements, continuous and closed intervals, do not apply. For example, if I have what looks like a reciprocal function, and if I want to find the area under the curve from a constant up to positive infinity, according to theorem 4.4, that's not allowed. The second case is, what about places where you don't have a closed interval or it's not defined at a certain point? For example, this rational function, is not defined at x equals 2, but we still might want to find the area under the curve between 1 and 3. And you might think that both of these green areas are infinite because the curve goes on forever, but that's not always the case. Sometimes they are infinite and sometimes they are finite. So finite areas can come from infinite bounds. The vocabulary that we use is that if the limit of a function does approach infinity, then that function diverges. All right, so the first set of examples deals with taking the antiderivative on an unbounded interval. So I'm going to start at a constant a, but I'm going to go up to positive infinity, or I'm going to start at negative infinity and go up to b, or I could go both bounds are at infinity, so from negative infinity to positive infinity. And what we're going to do to get around the requirement that we have a closed interval is we're going to replace that infinity with a letter and then take the limit as b approaches that infinite quantity. So infinity gets replaced with a variable b, and then we take the limit. Negative infinity gets replaced with a variable a, and we take the limit as a approaches negative infinity. And then for the third case, where we have two infinities, we're going to split this antiderivative into two cases, and the choice of c is arbitrary. Most often c equals 0 is used because then it's symmetric. And then we would take this first antiderivative and do it as if it was this situation, and then the second antiderivative would be as if it was this situation. So first you split, and then you treat each of these two like the previous two examples. So in the first example, we want the area under this reciprocal function, 1 over x minus 1 squared, from 2 all the way up to positive infinity. And if you go to your calculator and ask it to calculate this for you, you get 0.999999, which I think is 1. In other words, the picture for this is here's the reciprocal squared function. It does not exist at 1, and we want the area from 2 all the way up to positive infinity, and our calculator is saying that that area equals 1. So let's see what it is. Again, take the infinity symbol and replace it with a limit statement. So the b approaches infinity, so 2 to infinity becomes 2 to b. This statement, we're going to use a u substitution from this point in. Antiderivative of u squared is negative u to the negative 1. Again, your limits are different now. They're no longer 2 and b because we did a u substitution. Substitute back your function, so now we have negative 1 over x minus 1 going from b to 2. Plug in b and 2, and then take the limit of the statement. Well, if b approaches infinity and the denominator grows without bound, and we have 1 over large, which is 0, 0 plus 1 is 1, that converges. So this area, despite the fact the function goes on forever, this green area equals 1, which is pretty much what the calculator said. Second example, same kind of a situation, 2 to infinity of just a reciprocal function, not squared, but the reciprocal function. Same process, change infinity into b, take the limit as b approaches infinity. The antiderivative of this is the natural log of x minus 1. 2 to b, substitute in your b and 2, now take the limit as b approaches infinity. The natural log of a very large number is still a very large number, so we get an infinity minus 0, which is infinity. That one diverges. So what's interesting is very similar looking functions. One is 1 over x squared, one is 1 over x. This has a finite limit on the left. This has an infinite limit. So for now, there's really no way of predicting when we're going to get finite limits or antiderivatives, but when we're going to get finite areas and infinite areas. You'll learn more about that later in this chapter and a little bit more in the next chapter. So the next set of examples deals with open intervals. Instead of saying that we want the area under a curve between a and b inclusive, this one says we're going to go from a including a but stop just short of b. So since b is not on a closed interval, we need to replace b with a limit. So b is going to be replace with t, and we're going to say let t approach b from the left. Because we're going from a to b, we're going to approach but not quite hit b from the left. So again, the problematic part, the b, which is an open end, gets replaced with a limit statement, and we use the variable t and say let t approach b from the left. This one is intentionally left blank. I need you to look at this first one and modify the statement for when the left edge is open and the right edge is closed. And then finally, what happens when you have a restriction between your closed interval? For example, a function that doesn't exist at c. As I said earlier, you're going to split it up. Since your function doesn't exist at c, you're going to make c one of the endpoints of your interval, and then you're going to use the rules from the previous two examples here. So you're going to go from a to c, closed on a, open at c, and then you're going to go from c to b, open at c and closed at b, and use these two to evaluate this statement here. So pause the video, write up your answer to this part here, and then you'll check it in a second. So the answer's on the screen now. Because a is the problematic open side of the interval, you're going to replace a with a different variable t, and then have t approach a, but this time from the right. Because the right edge is defined, but the left side is not, you're going to approach a from the right. So last two examples. In this first one, 0 to 3 looks okay, but if you look, you can't let x equal 3 because then you'd be dividing by 0. So you're going to replace the problematic open end 3 with b, approach b from the left, and then take the antiderivative that way. So with the u substitution, u is 3 minus x, du is a negative dx. You have u to the negative 1/2 with a negative on the outside. Antiderivative is 2 u to the 1/2, replace your u with 3 minus x, and now you're going to evaluate this between b and 0, substituting in b and substituting in 0, you get these two values. What happens as you approach 3 from the left? As you approach 3 from the left, 3 minus very, very, very close to 3 is essentially 0. This term drops out, and you have negative 2 times negative root 3, or 2 root 3. This time, and these are the dangerous ones, because if you just plow ahead without looking, you might get a wrong answer. 0 to 4 has a domain restriction at 3, because at 3 this function does not exist. So you're going to need to take 0 to 4 and split it up into 0 to 3 and 3 to 4. So we have to evaluate both of these. Now there's a little bit of good news. If either one of these diverges, or if one of them becomes infinity, then you can stop, because infinity plus any quantity is still infinity, and that's what's going to happen here. So again, 3 is undefined, so you're going to replace 3 with a different letter b. You're going to take the limit as b approaches 3 from the left, because you're going from 0 to 3, you're approaching 3 from the left. Take the antiderivative, plus replace your 3 with a b, this time approaching 3 from the right. Going to work on that antiderivative. Both of those would have a u substitution where u equals x minus 3 and x minus 3 and du is dx. Set this up, take the antiderivative, you get negative 1 over x minus 3, substitute in your b and your 0. As b approaches 3 from the left, you're going to get a very, very, very small number here. 1 over very small is very large. This quantity evaluates and becomes infinite, so this is very large. We don't need to do the second one, because infinity plus or minus infinity diverges. So if you did wind up with infinity minus infinity, any kind of infinity statement diverges.